So in this video we're going to find a particular solution for a given Bernoulli equation. So just like in the previous video, before we go and use the technique for a Bernoulli equation, we have to justify that we actually have a Bernoulli equation. So I have my dy dx, here's the form of a Bernoulli equation. So it either needs to be in this form or you need to be able to manipulate it into that form to demonstrate that it's a Bernoulli equation. In this case, it's already manipulated into this form. We have the dy dx matching up. We have p of x times y, so 1 times y, so p of x in this case equals 1. And in this case, f of x times y to the n, so it's going to be 1 times y to the n, or negative 1/2. So f of x is actually equal to 1 as well. So it's a Bernoulli equation with p of x and f of x both equal to 1. And then that tells us then that we can use the Bernoulli equation technique to solve this differential equation. So we start by rewriting the differential equation. We have dy dx plus y equals y to the negative 1/2. And so we're going to multiply both sides by y to the positive 1/2. Whatever this exponent is, we're going to do the opposite of that exponent, because we want the y's to cancel, giving us a 1. So as long as y isn't 0, y to the negative 1/2 times y to the 1/2 is y to the 0, and y to the 0 equals 1 if y isn't equal to 0. Now distributing the y to the 1/2 into the parentheses, I get y to the 1/2 times dy dx plus y to the 1/2 times y to the first power is y to the 3/2. And then this is the step where we try to linearize it. We linearize the differential equation by setting w to the first power equal to that non-linear y to the 3/2 term. So we set w equal to y to the 3/2. So that's our first substitution. Then we need to figure out what w prime equals dw dx is. So I'm going to take the derivative of w dw dy with respect to y times the derivative of y with respect to x. So we get a dw dx equals, take the derivative with respect to y, which is 3/2 y to the 1/2, times the derivative of y with respect to x. So this is going to simplify to dw dx, which I'm just going to write as w prime. dw dx is w prime. I'm going to multiply both sides by the reciprocal of 3/2, so multiply both sides by 2/3, so that on the right hand side we're left with y to the 1/2 times dy dx. And then I need to use this and this for my substitutions. So here I have y to the 1/2 times dy dx, but y to the 1/2 times dy dx can be replaced with 2/3 w prime, plus y to the 3/2 can be replaced with w, and this is equal to 1. And now I have a linear differential equation in w. I want to get it into the form w prime plus p of x w equals q of x. I want to get it into the form that allows us to use the integrating factor u equals e to the antiderivative of p of x dx. So I need a leading coefficient of 1 on the w prime term. So we multiply both sides by 2/3, or sorry, 3/2. So 3/2 times 2/3 is 1. 3/2 times 1w is 3/2 w, and 3/2 times 1 is just a 3/2. So we get that by multiplying both sides by 3/2. And now we are in the form from the previous homework assignment where we solved first order linear differential equations. So our integrating factor is going to be e to the antiderivative of our p of x, in this case is 3/2. P of x is just 3/2, so it's going to be u equals e to the antiderivative of 3/2 dx, which is just equal to e to the 3/2 x. So The method for integrating factor is you multiply both sides by the integrating factor. So multiply both sides by e to the 3/2 x, e to the 3/2 x. And if we distribute, we don't need to do this, but if we distribute the e to the 3/2 x into the parentheses, we get e to the 3/2 x times w prime plus 3/2 times e to the 3/2 x times the w equaling the 3/2 times e to the 3/2 x. So if we've done the integrating factor correctly, then the term that we have here should be the derivative of the integrating factor e to the 3/2 x times w, and that's how you check your work. So e to the 3/2 x right here. Take the derivative of this product, the integrating factor u times w, and make sure that the derivative of it using the product rule gives you the previous line back. So the derivative of e to the 3/2 x times w is going to be e to the 3/2 x times w prime, which is showing up here, plus, using the product rule, now the derivative of e to the 3/2 x, which is 3/2 e to the 3/2 x showing up here, times the w term. So that work checks for us. That tells us we're doing things correctly. I have a derivative and I want to cancel that derivative so I get the stuff inside the parentheses out. So I'm going to take the antiderivative of the derivative. So when I take the derivative and then integrate, I'm going to get back the stuff on the inside. But if I integrate the left-hand side with respect to x, I need to integrate the right-hand side with respect to x. And when I integrate, I get a constant of integration on both sides that can then be combined into that single constant of integration. So now we just continue to work. Antiderivative of the derivative is going to give us the stuff inside the parentheses back. So we get e to the 3/2 x times w equaling the antiderivative of 3/2 e to the 3/2 x is just going to be e to the 3/2 x plus our constant of integration. And then if we're trying to get the w by itself, we'll multiply both sides by e to the negative 3/2 x, which is a much more efficient way of doing it than dividing both sides by e to the 3/2 x. We get e to the negative 3/2 x times e to the negative 3/2 x is e to the negative 3/2 x plus 3/2 x is e to the 0, and e to the 0 is 1. So we get 1 times w equals e to the negative 3/2 x distributed, e to the negative 3/2 x times e to the 3/2 x is 1, plus c e to the negative 3/2 x. And then once we've isolated the w, we want to recognize that we've actually made a substitution, so w needs to be converted back into the y world. So w equals y to the 3/2, so we just replace the w here with y to the 3/2 power. And now we have the general solution to the original differential equation. But because we're given initial conditions, we want to find the particular solution that goes with those initial conditions. So we're given the ordered pair x is 0, the y is 4, so we replace y with 4 and x with 0 in our differential equation, so we get 4 to the 3/2 equals 1 plus c times e to the, when we put a 0 in for x, we're going to get 0 times stuff is 0, we're going to get e to the 0, but e to the 0 is just 1, so we just get c here. So we can simplify the left-hand side. The 2 is in the denominator, so we're taking the square root of 4 and then cubing it. So the square root of 4 is 2, and 2 cubed is 8, so we get 8 equals 1 plus c. So that tells us that 7 is equal to the constant of integration. So substituting our constant back into our equation right here, we get y to the 3/2 equals 1 plus c, but c is 7, 1 plus 7 e to the negative 3/2 of x, and there's the particular solution to the Bernoulli equation.